Hello everybody, AOG Gaming here, back with another video. It's still going to be the quantum squared video, so we're going to be talking about, give me one second, quantum processors, computers, and basically all the advancements that I've been seeing so far in newspapers. I don't know if they have the best credibility, but it's all like research papers and companies. So I'm assuming there's some credibility to it, considering that usually when something scientific is posted and you can easily search it up and it's something like leading edge tech, it's pretty debunked pretty fast. Just like the whole superconductor thing at room temperature. Like there's been so many papers released and also debunked over and over again. So I tried to find papers that I believe are truthful and accurate, but take it with your own grain of salt or whatever you want to say. I know these are just like some random images here, so let's actually go to the first image I want to show you guys. So this one was blueprint for quantum computer in reverse gear. So basically they were, if you can see on the picture, so this little circuit down here, that's basically a basic multiplication circuit that you would see on any computer that we have today. Classical computers use that circuit, and it's basically used to just do multiplication. And what you see on top is what we call the quantum circuit version of that. I don't know if I have a better picture of this. Yes, I do. Okay, there you go. So it's a three-dimensional layout basically for how multiplication can be done with quantum mechanics, which is also why there's the second layer and then the third layer. Technically what's in between, so little x's would be like the answer, like where the answer would be, where the molecule would go to, the electron, I guess you could say, a photon, whatever you're using in the quantum computer, so that then you can process it on two different layers, because you have zeros, ones, and zeros, and you also have quantum entangled bits, which would be the zeros and the ones that are both, because when they're quantum entangled, well, actually it depends. They can be oscillating, they can be stagnant, but they can also be reversed. Very interesting how it works. It's a wonder why this tech is so complicated, and there's a lot of stuff going on with it. But yeah, this is just, for people who are trying to make quantum logic circuits. This was definitely something cool that the company showed. I forgot what company it was, but here is basically the entire layout. It's hard to see some of these. If you go to the actual paper, you'll probably see it better. University of Innsbruck. So just go to their website or whatever and look for blueprint for quantum logic computer in reverse gear or whatever. So that was pretty cool, because that means that now we're getting to the point where we can kind of make quantum computers classical and also do what we wanted to, where they're way faster, because now they can compute on a three-dimensional level instead of a two-dimensional level, if that makes sense. So basically with this circuit, it's like, the electron just follows the path and it goes there. But with quantum computing, it's a little different, and it just, like, I would have to explain how qubits and bits work, which, if you don't know how they work, I don't know why you're watching this video. Yeah, it's just the difference. So a bit can be a 1 or a 0, on or off, but qubits are a whole nother thing that can be 1 and 0, 0 and 1, 0, 0, 1 and 1, and then there's just a lot of things that they can be. The basic qubit, though, is a 0, a 1, and a 0, or like, flip, so a 0, a 1, or a 0 and a 1. So yeah, technically there's 6 states to a single qubit, whereas a quantum bit, or sorry, a regular bit, so like on normal computers on this phone right now, just a one and a zero. So you get three times the amount of computing processing power technically, but there's also the whole point of quantum entanglement and how that completely revolutionizes how we can use quantum logic and how we actually use bits like qubits, how they're actually going to be used in the computer and how they're going to travel. So just keep that in mind because it's very complicated. Um, Now, there's something called non-albion baryons. I believe that's what they're called. They're basically particles that can remember what happened to them, which is very cool. But they're actually not. Um, that's going too far. Did I take a picture of that somewhere? Yeah, right here. Nope, that's the wrong. Where was it? Here we go. Okay, so non-abelions, um, baryons, I believe that's what they are. Not or anyons, non-abelions, anyons. They're a special type of particle that can remember its past, which makes them less prone to errors. That's basically what this paper is talking about. They encoded them in ytterbium atoms or whatever. Ytterbium. I hate pronouncing scientific names. And as you can see, that entire, well, it's called a Tor shape or something. I forgot what it's called. Is there another picture fit? Okay, no. But basically, it allowed them to make or the particles remember their what happens to them, which is good. They remember basically their past states, which is good because it makes you able to compute for the quantum error because we still have to minimize that. But we are going to get that through that in this video because we are getting closer and closer to basically making quantum computing error proof. We're still, some ways from it, but it's getting like really, really close. And there's also chips that can basically do it at this point where they're isolating particles by themselves so that you can do quantum computing. The only problem is that the particle itself, like the quantum states themselves, fluctuate. So you do have to take into account whatever it's called, quantum fluctuation or the quantum. Just go watch the 11-hour lecture on YouTube if you want to really understand the depth of it. But basically, it just means it's going to be easier to account for errors in qubits and quantum computing, which is really cool. Now, next that I want to show. So, going off of that, so this was today that I saw this, but this was posted a few days ago. A quantum light source goes fully on chip, bringing scalability to the quantum cloud. So, at the University of Hanover in Germany, makes sense because I think Europe is kind of trying to become quantum supremacist or become the power in quantum power. Or I was trying to word that correctly, but me not know English, me no math. So it's very cool. I don't know if this is exactly how the chip works. It doesn't look like it because it's an artist illustration. But I mean the layout looks pretty similar to what it would look like. So you use the laser to basically um it doesn't touch other photons, but it goes near enough towards the photons that they induce um spin on each other because they are different wavelengths and charged, I believe, which makes them quantum entangled because I don't want to go too deep into it, but it has to do something with quantum colors and topological quantum, like the actual vibrations within the photons that are transferred to each other via the fields that each photon exudes from its charge state. Don't know if that made sense to you guys. It makes sense to me, but um, basically, so where you see the laser right here, it goes through this like green line, and then where you see the little white flash of light, that is the point at where these two photons become entangled, but they're not in the same loop or in the same. They are in the same system, but they're not in the same loop. So then that photon that's inside that first micro ring, the big one that's connected to this yellow part. Well, I can't really show you, but actually, I forgot that this was a thing. Um, can I? Nope, 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 nope. Did not want to do that. Can I like? Okay, well, pretty sure there's a way to draw. Oh no, I just have the pad, so yeah, okay, never mind. But yeah, so just the first ring, before you get to the other parts, would quantum entangle that bit, and then basically what happens now is that you have this single photon in a loop, and it can go to the next ring, which I'm assuming is a data transfer and scanner. So you would send another particle or photon that can quantum entangle with that bit, and now you can send it back into the computer outside of this quantum entangled chip or this quantum cloud chip. So then that quantum entangled bit, oh, and then you have this other part here. That quantum entangled bit is basically like now you know what that value is, and also with this one micro ring that has the first micro ring that has the quantum bit in it, it's stuck in that state because you're not introducing another photon to introduce another state of quantum entanglement, and therefore you can know what the value of the photon that you released back into the system is because you already know what its quantum entangled pair was before any errors or anything that would change the photon occurs. It's very cool. Um, and now there's some more complicated stuff over here, but yeah, as you can see, there's the blue and the orange dot right there. I can't really gesture towards it, but yeah, just imagine those two as photons basically. Except they wouldn't exactly look like that. I don't know why it shows it like that. And I'm assuming the other parts have to do something with quantum error and also storing the quantum states so that you know like which part. I mean, yes, obviously the particles are quantum entangled, so you know which ones belong to which other when you induce action on one particle and another particle changes in accordance to that. But when you're quantum entangling more than two um, pieces of information, which is possible, um, except it gets very complicated after that because then we get to the point where you can affect one. So let's say for example you have two photons that you have quantum entangled, but they're on two different paths. So now you split them apart, and they're quantum entangled, so they will act according to each other. But then you quantum entangle, you use only one of them, which is very interesting because you can entangle both of them, but then that induces change in both of them, which then induces change in all four of them before they settle down into their respective double entangled quantum states. I know I'm getting to the point where it feels like I'm just spitting out words, but it is how the logic works. But yeah, it gets very complicated. What you really need to take away from this is the fact that we're basically getting to the point where we can create quantum entangled systems of particles, and now we can bring them back into our computers so the quantum cloud is basically being scaled as the article itself is saying. Um, so it's very cool, but yeah, I can try and explain the rest of this circuit, but it's basically just accounting for error, and then making sure that those quantum states are saved, so to speak, or stored, so that you can know how the quantum state changes as it goes through the system, and so that you can accurately, you know, change the information, add the information, or compute it, or send it wherever you want, or store it. Very cool. Did I didn't take a picture of the other one. Damn it. Wait, I didn't. I'm pretty sure I did. Okay, well, I did not. But dang it, I'm pretty sure I took a picture of it. Well, that sucks. Anyway, moving on to what was it? Oh yeah, so also part of quantum computing and error analysis. So the Google quantum AI braids non-abelian anyons, which is what I was talking about before with the Deuterium Toron, or whatever the heck the shape is called. Just call it a donuts, but that's frowned upon in the science community. um, so basically, this AI did this, which is very cool, but it allows for easier quantum computing and also error um, minimizing. I can explain this, but this is a lot more theoretical rather than explaining how a particle travels through a path. So I feel like you guys should go read this paper by yourselves because it's very cool. But yeah, it kind of messes with your mind a little bit. That's all I have to say about that part. Oh, okay, yeah. So it was this one. Um, so I don't know. This is Business Insider. I don't know how accurate this is, but I did see this part and it was very cool. So the quantum part of the computer is right here, as you can see. It's got some laser gates, and it seems like they fused it with a normal computer, which is very cool. Um, so this is what I was talking about. Basically, fusing a classical computer with a quantum computer, because all that quantum computing really is going to do is do the bulk of the computations, basically getting down to, I wouldn't say perfection because we still have errors in quantum computing, but basically getting the computation down so that it's basically 99% accurate. And then to finish the computation, you do some less heavy algorithms on normal computers, classical computers, and all they have to do is basically either relay the information or transfer it, because most of the processing was done by the quantum computing parts of the computer. And then all you have to do now is send it through a classical computer and then display it on a screen. Because I don't know if there's a way to make this quantum display, whatever that would sound like. I mean, we have quantum LEDs, but I mean, they still turn on and off. Like the way those work aren't the same as it's just, I can't explain it, but it's hard to make a display that can make use of the six different states that a qubit can be in, because our eyes can only see on and off, really. Like the light is either there or it's not. Like it can be blinking back and forth, but that's just refresh rate at that point for us. Like you just increase the refresh rate and then you don't see the parts when the light is off, which is 60 hertz if you didn't know that. But yeah, it's just interesting. But it makes sense. Like I was telling you guys, you have to fuse the quantum part of computers with the classical computer first, so that we can understand how we can make quantum computers viable for everything. Um, because honestly, they will help everything, not just science and math and technology, but like your daily life. And it all comes down to AI, obviously, because AI is going to be a very big part of our futures. Um, Next thing, part of quantum computing. A lot of stuff I get is from physics.org. They're pretty reliable. They haven't had any like papers that were proven wrong or anything like that. Now we're talking about graphene in boron nitride. Um, so it's just basically, if you look at that, this is basically the state's. Oh, that's very interesting. Yeah, so this weird, like angle, the magic angle or whatever they call it, allows for very easy transference of electrons. And as you can see, there's these, well, there's 7 spots where I believe you can trap electrons in. So they're kind of like electron traps, charged particle traps, whatever you want to call them. And what this allows is that you can isolate electrons now, and then they also have the property of what was it? Zero electrical resistance. So no heat loss, and it doesn't take as long technically for the electron to move through the circuits. So it's very cool. Um, so I'm not going to go too much into depth to it because then I have to explain what a phonon is and how that works with graphene. Basically, what you have to keep in mind is the electrons. I guess we'll just call them phonons. Absorb the energy from the electrons. That's why the energy dissipation to the phonons, that's what it's saying, goes onto the graphenes. And you can think the electrons are on the boron nitride film. Because, yes, technically, graphene does have those pi bonds, sigma bonds, pi bonds, the bonds with the free electrons, but it doesn't necessarily mean that they can carry like any amount of current. What was I going to say? So yeah, so the energy is dissipated to the phonons in the graphene, which you can think of just as the sigma bonds, basically, or pi bonds, whichever ones they were, the ones that aren't bonded to the carbon atoms. Then the phonon back action, which is the polarity of the actual phonons, induces charge on the electrons, or it basically repels or pushes the electrons, which induce um, basically electricity. So the electricity can go through. So it's very cool, but I you have to read the paper. Just read the paper and you'll understand more in depth. But yeah, it's very cool, and basically what that means, it's we're getting closer to making graphene as part of quantum computing, so that it's much more efficient, and also just for normal like classical computers, so that it's much more efficient and it's easier to work with. I don't know how expensive it was to make that graphene because the process is dangerous and expensive, but to each their own, and also, in the name of science, whatever they say. So I believe that's it. There was a few more photos here that I want to talk about. Mostly about this highly multicolored light emitting arrays for compressive spectroscopy on a chip. The reason I'm talking about this is because they basically made a 489 array of different lights, different wavelengths, which is very cool because if we're able to basically include this into quantum computing, now you have a chip, whatever this spectroscopy chip, you can use that to change spin of electrons. I don't know exactly how that would work, but you can use already lasers to hit electrons and change their spin, which allows you to compute with electrons using photons. It's very interesting. But I think that's like the next part of quantum computing, where we use the photons not only to quantum entangle them, but quantum entangle electrons, and then those electrons just go through a classical computer and give us an output. But all of the quantum computing is done within the quantum computer, so that all of the entangled states are just arbitrary values that can be directed to a screen, and it's either on or off the LED, which is very cool. But yeah, I don't know how hard this is going to be, but yeah, I fabricated a 7 by 7 array of devices with different wavelengths. It's very cool. But yeah, we're getting to the points where we're close to building a quantum computer that can do all of the calculations for us with basically 0% error, and then just send it through a screen, basically, which would be a classic computer that's just turning all of that information into values that are simple enough to display on a screen. But yeah, very cool. Awesome. I'm waiting to see what more stuff is coming, but yeah, I think that's it. That's all I have. Whoopsies. Yeah. Um. Okay, that's something interesting. So if you see this picture here, that's what most foolproof, like fully built quantum computers look like. They're just very big and bulky, but all this can be downsized to the nanoscale. Just very hard and extremely laborious and also dangerous, which is why you need machines to do that. Um, yeah, I think I should stop here because now I'm just gonna continue talking about random stuff if I find another article. Yeah, and then there's a problem with quantum safe cryptography because like we're getting to the point where AI might be just be able to completely compute everything that we're sending through the quantum cloud, which makes it not safe. But yeah, we're getting closer and closer. So yeah, keep your fingers crossed, guys, and hopefully they already have quantum computers available for sale, but they're pretty big and they're not. It's like 432 qubits or something like that, which is sounds like a lot, which it is for now, but it's nothing compared to what a classical computer can do. But they're also very different in how they compute and work. So do keep that in mind. Anyway, thank you guys for watching. ALG Gaming here. If you're enjoying the content, please like and subscribe. Really shows your support. Helps me out, keeps you up to date with my content. 61 subscribers and going strong last time I checked. So you guys are amazing. Keep going. Yeah, that's all I have for this video. I don't know if this series will continue. It depends on how fast we develop quantum computing. But yeah, thank you guys for watching, and I will see you guys later.